Hello, Jesse.
Hello, Alan.
How are you doing?
Fantastic. How about yourself?
Great, great, great. We're making progress slowly but surely, as usual. And yeah, we're just walking step by step through the consensus programs and developing things. And yeah, I guess that's a very poor segue into the topic that I wanted to talk about, which is non-deterministic programming. So, um, we don't live in a non-deterministic world. Everything has a definite value, excluding perhaps quantum wave functions, but non-determinism is the behavior of a theoretical construct of computers where they explore all possible worlds at the same time. Um, and it turns out that this theoretical model of computation is exactly the model in which provers live. And so, whenever you write a program that can be proved, or with the intention that it will be proved, you have the option of supplying a part of the input, or perhaps even all of the input, as non-determinism.
I'm not sure I understand why that follows.
Well, non-determinism means whenever the computer has to make a choice, it makes both choices at the same time. Um, and input means you read something from your input stream, and based on that information, you make a choice left or right.
Okay, so
Uh,
non-determinism is that it always chooses all options. It's not that it just chooses a random option. That's not also non-determinism.
in computer science, non-determinism refers to choosing both options.
You say
The,
both. Is it always two?
well, in a simplified form, I guess you could
Sure.
define it more generally, but two is the smallest possible selection of options that is still meaningful.
Yeah,
Um,
that part I understand.
that part you understand, yeah. And so, from the prover's perspective, he just needs a criterion to choose one of two branches. It could, and the criterion could be coming from explicit input, or it could come out of the blue
No, no, but
through divine
back
intervention.
up because you started off saying we live in a deterministic world.
Yes,
And so you've got a proving mechanism, and
yes.
then therefore that proving mechanism can be non-deterministic. That's how I felt the logic went. But I
Well,
don't.
the you describe the code of the prover in exactly the same way as you would describe average computer programs if you were to live in a non-deterministic world. So you read a symbol from the blue sky through divine intervention. It happens to be exactly what you need, and then you proceed with that. But then the catch is, since we're living in a deterministic world, you need to boot this prover inside of an
Okay,
environment
okay, so
where the
okay,
correct symbols are actually
so
supplied.
you're saying we are living in a deterministic world. Inside the deterministic world, you would like to build a non-deterministic prover, and to simulate that, you the problem is that you're still relying on deterministic mechanics. You need to somehow simulate that non-determinism. That's what you're saying.
Well, I'd say simulating the non-determinism comes for free, but By free, I mean if you look at the cost metric, it's actually the mechanics of proof systems. They are expensive whenever you constrain down the evolution of a system, and whenever you release those constraints, they become cheap. So yes, getting the prover to make use of the non-determinism is for free, but the trouble is typically, can we find a translation of an algorithm that is faster if we make use of non-determinism,
Okay,
or
but
that achieves things that otherwise we can't?
why are we interested in non-determinism?
Well, for starters, maybe you want to prove something about secrets. Like, I know the pre-image to this hash function, and by demonstrating that I know the pre-image to this hash function, that happens to be the rules that I encoded, that I encapsulate, that I locked my UTXO to. And so I would be able to spend money by unlocking UTXOs, by proving that I know the pre-image to a hash. And then where does the program
But
that I'm going
isn't
to
it,
run
sorry, isn't a
in prover
hash
mode?
deterministic?
The hash is deterministic, but the program that proves that, I guess I should make a distinction between the program and the prover, right? What the program does is it evaluates the hash function on some non-deterministic input and produces the output explicitly. The prover therefore proves knowledge of the preimage of that digest. And the problem is that you can only, or maybe the feature is that you can only run this prover in an environment where you are actually supplying the correct preimage. And so only the owners of UTXOs can sign off on their expenditures.
Okay, so let me feed that back to you. So you've got a program which is basically a hashing program, right? It hashes some image, and you want to prove, hey, I know the algorithm, or I know the image that was
The
before
pre-image,
the pre-image before
yes.
the hash. And the thing that you use to prove that claim is a prover, and then somehow non-determinism comes in. I'm not sure I
Yeah.
understand that
So
part.
the way you write this program is to say, let variable x equals divine intervention,
Yeah, that's the
hash
non-deterministic
x,
part.
output the result. And the divine intervention is the non-deterministic part, yes. And then when you run the prover, you actually need to ensure that the right information is available.
But why is that? I mean, you say, but I mean, could you not just phrase that in deterministic terms? You say, this program is a function. It takes any input argument, and the output is the hash of the input argument. I'm still not
And
sure about the non-deterministic part.
well, if you take that program and prove it, then you will need to supply an explicit input. And if I want to verify your proof, I will need the explicit input as well. And so all you need to do is send the pre-image to me. Thank you. Now I can spend your UTXO.
Okay, so hang on. So there's a hash of a pre-image, and I'm claiming I know the pre-image. How can I prove that?
You run the program that I described in prover mode. And the program that I described is let x equals divine intervention hash x output result.
But the program you're describing is not A hash function.
It's a very thin wrapper around the hash function.
But what does it do?
It outputs the image of some preimage under the hash function. This particular
But how?
program has no counterpart in the deterministic world
But how does it prove that I know the pre-image of my hashing operation?
because otherwise you would not be able to successfully run that program in prover mode.
But what does prover mode take some input?
So it takes an explicit input. In this case, that's empty, but it also takes a non-deterministic input.
But what
And
do you mean? What do you mean by otherwise you would not be able to run it? Like what makes it that I can run it?
yeah, you supply this pre-image as the non-deterministic input to the prover.
But the pre-image is deterministic. It's determined. It's the pre-image. That's what it is.
Yeah, so the non-determinism only lives within the perspective of the prover, right? As the UTXO spender, you can invoke the prover as a black box, and from your perspective, the world is deterministic. And so you wrap this black box inside of an environment where the non-determinism is actually defined and determined. From the
But I'm,
perspective
I'm
of the
still.
prover,
I
it's
think. But
non-deterministic.
I think even the part about it being a transaction is just information we don't really need at this point. We could just say it's something valuable. But what I'm still not understanding is how that prover would work. How does it work with the pre-image?
Well, in the end, you supply two inputs to the prover. One is the explicit, we call it the standard input, and the other input is the non-determinism. And so in this particular example, the pre-image would go into the non-deterministic input.
And the second input is empty.
Yes.
Okay, I still don't understand what it does. I mean, the end result is that someone looking at it can see, oh wow, he wasn't lying. That does indeed know the pre-image, right?
Yes.
Okay, but I'm still not clear why non-determinism has saved the day.
As opposed to
Uh, I don't
this
know.
particular program, it doesn't have a deterministic counterpart. So there's no way to drop non-determinism and still have a working
No, but
example.
you were saying, listen, here's this thing that one party can view it as a black box, and then the other one that can sort of go inside the box sees that there's two inputs. One is the pre-image, one we're leaving empty, but still something happens. To me, sounds like another black box, and then the proof emerges, and somehow that shows us that non-determinism is useful. So I'm missing a lot of information.
The programming language in which you write this non-deterministic program, it can make appeals to God. That's the feature, right? It doesn't need to know that God does or does not exist. It doesn't care where the input comes from, and that's why we call it non-deterministic input. Where it comes from is not determined, rather than purely theoretically, it takes all branches simultaneously. But in order to run that program in prover mode, you actually need to determine the non-deterministic input.
Okay. You determine the non-deterministic input only in prover mode.
Yes.
And what is prover mode?
Well, where you're going to output a proof.
And what other modes are there?
Standard programming mode that we've known before proof systems came along.
In which case the non-deterministic input is actually non-deterministic.
No, in which case non-determinism doesn't exist to begin with.
Okay, so now I'm confused on another level. So the non-deterministic input only exists in prover mode, right?
Yes. Yes.
But it's not actually non-deterministic because we determine it because we know the pre-image.
Yes.
So if it doesn't exist in the non-prover mode and it doesn't actually exist in prover mode, so where does it exist?
And yet I can still write programs that make appeals to God. So why don't you explain to me why it's still possible for me to write that program and execute it?
Well, to me, it's right now based on my mental model, which obviously is lacking. It doesn't sound like it would be worth it because it sounds like it's the same thing as in non-prover mode. So I'm still not
Because it's still
understanding
being
the
determined somehow.
yeah.
Well, maybe the right way to describe things is saying the non-determinism is just another input, but it's segregated from the standard input in a way that leverages the proof system's zero knowledge property. And so you leak zero information about the non-determinism. But it's really just another input.
I think we need to or you need to try and find a different way of explaining why non-determinism is such an essential feature, um, rather than saying, "Oh, we can appeal to God." I think that the part that you can invoke non-determinism, that's clear, and that sounds profound. What's not clear is how that changes anything.
Okay. Different example. Suppose you have a more complicated program, and in the course of that more complicated program, you produce a list and you need to sort that list.
Yeah.
And it's a huge list. So the complexity of sorting is n log n with the best possible algorithm. And you really dislike that log n factor. So can we do any better? Yes, we can. Because what you're going to do is you're going to supply the sorted list through the non-deterministic input. You define the sorted list and you verify that all the elements that are present in one are present in the other, and that the
What
sorted
other?
list
What
have.
other?
You produce one list and then you define a sorted list.
A sorted list, yeah.
And then you verify that they match as sets, and then you verify that the second one is sorted by comparing every consecutive pair of elements.
Okay.
And if you do the maths, you'll find that that only costs O of n work. So you've saved a factor n, excuse me, you've saved a factor log n work.
Sorry, the difficulty calculation in the end, I'm not sure I understood. What difficulty are you calculating exactly at the end?
The amount of work performed by the program.
But what work is the program performing? Because you've supplied it with the ordered list.
Well, it's doing something else after verifying that the list is sorted with that list.
Which is what?
Inserting all the elements into a different list.
I'm not, okay,
That
and this has somehow,
second-hand application doesn't matter.
but somehow this is supposed to help us understand non-determinism.
It's another example that explains why it's useful.
Okay, to me it sounds like you said you've got a list that you want to sort, which but it's somehow because of the nature of the list, it's very difficult to sort. So it takes a lot of computational resources.
It's because of the nature of sorting.
Nature of sorting. So you plug it into your prover or proven program
Yes, prover is fine.
as the non-deterministic. No, you the sorted list is the one that you invoke divine intervention. So that would be the non-deterministic input,
Correct.
and the list itself would be what the other input.
Yes.
Okay, and then the
Then you do whatever follow-up tasks were defined by the context to begin with. And so the running time of your algorithm is dominated by O of n as opposed to O of n log n.
but that proves that there's a faster sort is possible, or what does it prove?
It establishes that sorting can be done in n time in a non-deterministic model of computation.
Yeah, so what I don't understand here is maybe there is something like non-determinism that you can invoke and perform calculations with. What I don't understand is why would it be that you can start with sort of the where you start with, so with unsorted list, you can plug in where you want to end up the unsorted list, and then by some magic the algorithm outputs the complexity of some sorting algorithm that you do not yet know, but then somehow by doing that you know that it exists. How is any of that possible?
So you still have to sort the list, unfortunately, but you sort the list before you start the prover. And so the n log n cost of sorting the list happens outside of the entire prover mechanics pipeline. And since running the prover is the expensive part, that's the cost that you're trying to shrink down to the smallest possible number.
But are you so you're not proving that the list was sorted, because that would be easy. But you're proving that an algorithm exists with a specific difficulty to sort that list.
In which
Complexity.
sense of the word are you using proving right now? Right?
I'm the
There's a
one that's
mathematical
lost.
sense, excuse me, there's a mathematical sense in which you posit a theorem and then prove it, and then other mathematicians will either accept or reject your proof. And there's a computational sense in which your computer outputs data. In the
Okay.
mathematical sense, I have proven that there is a O of n time algorithm for sorting lists in the non-deterministic model of computation. In the
But
computational
but
sense,
how
well,
how how
it
does, how does that
the
emerge?
the program divines the sorted list and then verifies
No,
its
you do
correctness.
that. You do that. You make the program do it? I thought we supplied that.
No, no, no. We make the program do it. We write the program that operates in this way: divine a list, check set equality, verify that the defined list is sorted. and
Okay,
then
but
output it.
let's try again. Repeat that last part, please.
So the theorem is, in the non-deterministic model of computation, the task of sorting takes O of n time. And to prove this theorem, what I need to do is supply
So
a
you
computer
start.
program
You,
that achieves it.
okay, you start with a theorem. So you start knowing that sorting with a lower complexity is lower difficulty is possible.
Yes.
So that doesn't emerge from the proving. It's not like, oh, here's some
No.
very difficult task. Let's throw in the prover, and the prover says,
No,
hey,
no, no,
actually,
no.
okay.
This theorem emerges from our confusion about what proving means.
Okay. Okay. So then again, rewind. So
And so, if we're talking as mathematicians in terms of theorems and maths proofs for them, in order to prove this theorem, I need to supply a computer program in the non-deterministic model of computation that sorts lists in O of n time.
okay, you need to. So what do you end up doing?
I just presented this program. You define the sorted list, check set equality,
What does
verify
that mean?
the sorted list.
Check set equality. Oh, that means that all the elements are yeah, okay, in both
Yeah,
lists. Yeah.
exactly. Uh, Check that the defined list is sorted and then output it.
But without specifying what the sorting algorithm is.
Indeed, you can think of it as being implicitly specified by the check that it is sorted. But yeah, there is no specification of mechanics to obtain a sorted list.
And
That's
is
true.
there specification of what the sorting difficulty is?
That's not emerging from the proof system. That we know from theoretical computer science.
So I feel like I'm still tripping over. Like, okay, I understand what you said. So you got a proving system. You input the sorted list. You input the original list. You make sure that all elements are parts of both lists, and that the sorted list is indeed sorted list. You're operating in the non-deterministic. What did you use? World of computation.
Model.
Yeah. Um, some magic step, and then okay, some like that indeed it can be sorted with that complexity. What's happens here? What's going on there?
I'm not sure which magic step you are referring to.
Okay, I mean me neither. It feels like there's some information. It doesn't feel like like a fully coherent mental model.
Well, maybe what you're looking for the words for is the question: where does the sorted list come from?
I mean, but you could sort it inefficiently. That part is not.
Yes, you can sort it inefficiently. That's the clue. And you pay for the cost of this inefficient sorting in the end because we live in a deterministic world, yes, but you don't pay it through the prover. And the prover, the complexity of the prover, that's the one we care about because as you produce proofs, you just incur a lot of computational overhead.
Let me see a different angle of what I don't understand, and maybe we need to stop after that and then pick up next week. But a different angle on what I don't understand is that you've got some system that you're describing, this prover function, a prover system, and you're only supplying it with a sort of before state and after state, and that's what I'm hearing. And then somehow,
That's a very concise summary. Yes.
it's able to tell you something about what happens in between, even though you're not supplying that information. So I don't understand how that's
And
possible.
it's not even necessarily capturing mechanics of evolving from one state to another. It's just capturing the relation between those two states. Yes.
But you're agreeing with my question. You should be answering my question.
Okay. Can you repeat the question,
But
please?
the question is, I don't understand how that's possible. But I presume that the answer involves invocation of non-determinism. But I don't understand how that's possible. Maybe we pause here for this week. I continue to think about what you said, and you think about a way to dumb down the answer to that question.
That sounds great. All right. I look forward to the follow up.
Okay,
Take care.
cool. Yeah, me too. Take care.